Good morning guys, we are the group 6 and our topic for today's lesson is quadrantal spherical triangle. So may I call on Gilbert Morales to discuss what is quadrantal spherical triangle.
What is quadrantal spherical triangle? A quadrantal spherical triangle is a type of spherical triangle that occurs on the surface of a sphere such as the Earth. A spherical triangle is a figure formed on the surface, a sphere by three great circle arcs connecting three points that do not lie on a great circle. In the case of quadrantal spherical triangle, at least one of the angles of the triangle is a right angle, meaning it measures 90 degrees. The term quadrantal is derived from the Latin word quadrans, meaning a form, part, or a quarter, and it is used to describe an angle that spans 1/4 of a circle or 90 degrees.
So may I call on Generosa Sergio to discuss further what is quadrantal spherical triangle.
Quadrantal spherical triangle. To understand the concept better, imagine that sphere such as the Earth. If you have 3 points on its surface, the great circles arcs connecting this point from a spherical triangle. If one of the angles of these triangles measure 90 degrees, then it is quadrantal spherical triangle. Spherical trigonometry is the branch of trigonometry that deals with the relationship between the sides and angles of the spherical triangle. It is used its various fields including astronomy, navigation, and geodesy to make calculations on the surface of the sphere.
So what is quadrantal spherical triangle? So the term quadrantal in the context of a quadrantal spherical triangle refers to the presence of a right triangle, which is an angle measuring 90 degrees. In geometry, a right angle is often associated with a quarter or 1/4 of a full circle. As a circle has 360 degrees and a right angle represents 1/4 of the total. So only one exception from side angle spherical triangles. So if the adjacent or opposite parts are both angles or both sides, then an extra minus sign must be introduced. So may I call on Daniel Tampus and Archaga Axel to discuss what is Napier's rule.
Napier's rule is a trigonometric rule developed by Scottish mathematician. This rule is particularly useful when solving problems related to quadrantal spherical triangle.
The purpose of Napier's rule in solving quadrantal spherical triangles lies in ability to relate the sides and angles of spherical triangle when one of angles is a right angle. Specifically, Napier's rule relates the lengths of the sides of quadrantal spherical triangle to the tangents of half the angles.
So in our sample problem, in spherical triangle ABC, side C is equals to 90 degrees, angle B is equals to 14 degrees in 20 minutes, and side A is equals to 110 degrees in 11 minutes. So find angle C and side B. So we have here our spherical triangle. So here's our side A, which is equals to 110 degrees in 11 minutes. And our angle B, 14 degrees in 20 minutes. And our side C, 90 degrees. So we're going to find the angle C and the side B. So we have here our Napier's diagram. So we at the top of the circle, we have the angle C is equals to 90 degrees. We're going to make a two semicircle. At the top of the at the top semicircle, we're going to put the angles next to the angle C, which is the angle A and the angle B. And at the bottom semicircle, we're going to put the angles opposite. So the opposite of angle A is the opposite of angle A is B. So we're going to put B. That's why there's 90 minus B. At the right side of the bottom semicircle, we have angle A, which is opposite to the angle B. So 90 minus A. So in the middle of the bottom semicircle, we have the remainder angle, which is C. So 90 minus C. So first, we're going to find the side B. So to find side B, we have sine parenthesis 90 minus B is equals to cosine B, then cosine parenthesis, open parenthesis 90 minus A. So cosine B is equals to cosine B sine A. The next, cosine B is equals to cosine, then the angle B, which is 14 degrees and 20 minutes, then sine, and the angle A, which is 110 degrees and 11 minutes. So next is cosine B is equals to the answer of the cosine 14 degrees 20 minutes, which is 0.96887, multiplied to the answer of the sine 110 degrees 11 minutes, which is 0.93859. So after, we're going to multiply 0.96887 to 0.93859. So next is cosine B is equals to the answer 0.90937. So B is equals to cosine negative 1 parenthesis 0.90937. Then the final answer is the side B is equals to 24 degrees and 34.9 minutes. So next is to find the angle C. So to find angle C, sine parenthesis 90 minus A is equals to tan B multiplied to tan parenthesis 90 minus C. So both angles, so introduce an extra minus sign. So sine parenthesis 90 minus A is equals to tan B, then tan parenthesis 90 minus C. Then we're going to put negative 1 since they are both angles. So next is cosine A is equals to negative tan B, then tan parenthesis 90 minus angle C. So next is tan parenthesis 90 minus C is equals to cosine A divided by negative tan B. So tan parenthesis 90 minus C is equals to cosine 110 degrees and 11 minutes, which is our angle A, then divided by negative tan 14 degrees and 20 minutes, which is our angle B. So we have here tan 90 minus C is equals to the answer of cosine 110 degrees and 11 minutes, which is negative 0.34502, then divided by to the answer of negative tan 14 degrees and 20 minutes, which is negative 0.2552. The next is tan 90 minus C is equals to the answer of negative 0.34502 divided by negative 0.2552, which is 1.35027. So 90 minus C is equals to tan to the power of negative 1 multiplied by 1.35027. So 90 minus C is equals to 50 degrees and 28.6 minutes, which is the answer of tan to the power of 1 multiplied by 1.35027. So we have here angle C is equals to 90 degrees minus 50 degrees and 28.6 minutes. So we have our final answer. So our final answer for the angle C, so angle C is equals to 36 degrees and 31.4 minutes. So test yourself. Solve the right angle spherical triangle ABC we have our given side C is equals to 90, angle A is equals to 105 degrees in 11 minutes, and angle B is equals to 60 degrees in 18 minutes. So that's all for group 6. Thank you for listening. Army, Pipito Cyprus, Archaga Axel, Generosa Sergio, Morales Jobert, Bautista Ken, Tampos Daniel.